Hello, my friends. Welcome back. In the previous videos, we talked about regression models, right? We saw some examples of linear regression models, polynomial models, and nonlinear models. And we also saw how we can actually use neural networks for regression purposes. Uh, and I thought it's a good idea to move on to the next topic in this video and talk a bit about classifiers in Python, right? We will be seeing examples of support vector machines and neural networks as classifiers mostly. Um, and let's get started. Again, like in this course, I don't really want to dive deep into the concepts like what is a support vector machine or how does a neural network exactly work. It's an advanced topic. I'm just going to show you how to use the libraries, and I will eventually make a new playlist about machine learning because it's a hot topic and everybody needs that and it's very useful. And in that course, I will be going over the details and like explaining everything and all the concepts. But in today's video, I'm just going to focus on how we can use them. Okay, let's get started here. As always, we start with our imports from matplotlib dot pyplot. Wait a minute. Pyplot as plt, and from scikit-learn. What do we want from here? Import. The first thing I want to import is the datasets because in the previous videos we used some data stuff, like we downloaded datasets from Kaggle website. You can use whatever dataset that you want. Today I'm going to be focusing on the handwritten digit dataset, and scikit-learn already has that. It's in the dataset, so I'm just going to use that. And support vector machines and neural networks. This is what I'm going to do. We also want to, from scikit-learn dot model selection, you've seen this before, import train test split, right? That's what we want to do. Let's get started with loading the data set, right? We can comment our code here as well. It says loading the data set, and we can go digits because it's a data set of digits. That's datasets dot load digits. It's here. Just as simple as that. Like digits is like a data set. Scikit-learn knows that, and I'm just like loading that data set. And let's just see how that data set looks like. You can just go print digits dot data dot shape. If you don't know like what happens when you use this, it returns like a digit object. It's a structure with different fields. It has data, it has target. You can look it up and like to see more details in here, but I've already worked with that, so I know what I'm doing here. But yeah, as I said, it basically has two fields in it: the data, which is the images, and the targets, which are the labels, right? So you see an image, and then like because it's a supervised learning model, it has a label. It needs to learn based on that, right? Anyway, let's not get very much involved into the details. If I run that, it says it's a data set of 1797 samples, and each sample has a size of 64. Again, it's a database or a data set of images. Each image is like 8 by 8, right? That's why we have 64, elements for each image. And then we have 1797 samples. All good. We can actually, like, if that helps, we can try plotting one of the images. We can go plot that image show because it's an image. And then I'm just gonna go digits dot, not the target, but the image, right? Images on I don't know, like image number 101. We have like 1797 images in here, so you can choose any of them. And then, yeah, we can just like plot that, and then we can just give it a title, plot that title. That's, we want to know, because like sometimes you cannot really read that. I just want to go for the title, use digit, and I just want to type what digit it is. So it's digits dot target 101, right? And plot dot show, that's not how you're supposed to show. Okay, let's see. If I run this now, it's taking its time. Okay, so it shows something. It says, okay, like this is the image that I'm looking at. See, sometimes it's really hard even for us human beings to read that, right? And it says, okay, this is digit 0. This is the label that I'm printing here. See, digits the target 101. And then this is the actual image. And then like you can, this is a cool function. You can play with that. Like if you want, you can just go, for example, CMap for color map, that equals plot dot color map dot gray, I think, underscore R. That just like show the image in the grayscale format, which is like usually more useful when it comes to classification tasks, because it reduces the data size and stuff. It reduces the complexity of the model. Anyway, so this is like an example of the image, of one of the images in our data set. We don't need this. Let's just comment this out for now, and let get started. So the first step we need to do is to like clear our data, like make it ready for our models. So I'm just gonna go number of samples that I have. Great, that equals length of, you already know that, right? Digits dot images, right? Okay, length of that, it just gives me the number of samples in my dataset, which I already know that. I know it's like 1797. You can print that to make sure that you're not wrong. And now I want to go data, which is like the actual data that I want to like use for training and test purposes, is digits that images, right? I'm going to get the images. And because each image is 8 by 8, right, I cannot really process that. I need to flatten my data. Let's actually like put a comment here. Flatten, that's too many P's, flatten data. I want to convert an 8 by 8 array into a one-dimensional array of 64 elements, right? So I'm just going to go reshape that with number of samples and -1. So if I do that, right, let's see if that works, if I haven't done anything crazy. Okay, that's good. And now if I go print, for example, data 0, because like data has now 1797 samples, and each of them is like 64, an array of like a 1D array of 64 elements. So if I do that, I should be able to see like a single array with 64 elements, which are the pixel values for my image, right? If I run that, and that's exactly what I see. It's 64 to make sure. Let me just like do a quick count. Yeah, so 18 elements, and it showed 3 rows, 3 by 18, that's 54. And here, yeah, that's exactly 64 elements. Okay, so far so good. Our data is ready to be used for training and test purposes. Okay, we can just comment out our extra prints because we don't really need them. Now we want to create a classifier. Create a classifier, right? We can go see a lot of the classifier that we have, and classifier 1 because I want to define number 2, one for support vector machine and the other one for neural networks, right? So SVM, right? The thing that we imported up here, support vector machine dot SVC, support vector classifier. That's what SVC is short for. And like, again, I don't really want to dive deep into the concepts on how exactly support vector machine work, but if you're already familiar with that, you know, like there's a gamma factor. I'm just gonna go gamma equals, like it has a default value probably. Let's see. So it's a floating point value. Yeah. Okay. Anyway, we can just like give it a value. It can just be like, it's that maybe. And the second classifier, right? It's we imported neural networks. So from neural networks, we want to bring MLP classifier, right? And for NLP multi-layer perceptron classifier, we can define a solver, and then we can just give it a name, OBFGS, I think. Yeah, here you can see like solver options. You can use LBFGS, you can use SGD, you can use ADAM. You can use any of them. Like, let's just use ADAM for now. Yeah, let's just use ADAM. It doesn't matter. You can use like either like each of one of these and just play with them, see how like that affect. But again, like I don't really want to get into that, like how ADAM is different from SGB and stuff like that. We just want to see examples of how we can use them. So that's the first element, input argument, and there is like a learning factor alpha. It's a float, and you can see that it has a default value set to 0.0001, and so we don't even have to provide that, but we can just like go, okay, like change it like that, just like an order of magnitude larger than what the default value is. Just why not, you know? And then you have to define the architecture of your neural network, right? You have to give it the number of hidden layers and like how many hidden layers do you want. I'm just gonna go 50 by 10. So it means that I have 50 neurons in my hidden layer and then 10 for my output layer because I have 10 digits. Like those are the number of classes that I have. So an input image comes in, it's either 0, 1, 2, 3, or I'll look all the way to 9, which is like 10 different classes. That's why I need 10 in here. Okay, so those are our two classifiers, right? Now we want to train the two classifiers, the first one and the second one, and compare, see which one works better. Now that we have that, the next step we do, as always, is to split the data, right? And we can go X train. We've seen this before. X test and Y train, Y test. That equals train test split, and then data. That's the thing that we want to split, and digits. The target. Okay. So this is like X values, right? The input images that we want to train. These are the Y values, right? The actual value that we want to predict and compare against these values. And then the third one, as always, is the test size. We can just go 2.2, which is like use 20% of the data for testing and validation, stuff like that, and the 80% for training purposes. So that's good. We have that. And now we can actually learn our model here. Okay. This is also like a very simple process. We can go CLF1 that fit very much like the regression models that we saw, right? That fit, it start training the model. You have to provide the training data and the training labels because it's a supervised learning research. So X chain and obviously Y train. And we can do the same thing for CLF2. Again, so you won't be confused. CL1 is the one that uses a support vector machine. CL2 is the one that uses a neural network. We're just like training both models with the same data, right? So our models are trained now. And now we want to predict, right? Predict. And here we can just go predicted for SVM. That's equal CLF1, right? Classifier 1 dot predict. We also saw that when we were talking about regression models, right? Same function. Honestly, it doesn't really matter. Is X test, and we can just copy that and paste it so that we won't be wasting time. And I'm just going to call that MLP because we're using a multi-layer perceptron neural network. So I'm just going to call that MLP, again, with the same thing. So it's going to be classifier 2 predict, and we just want to test the same data there, right? And let's see how it works. If I run that now, see if it's happy with our implementations or not. Okay, it ran it. That's cool. So we have a working model now, and it's working. It's not at least complaining about anything. Now we want to compare the accuracy, right? How can we compare the accuracy? We cannot use mean square error or, I don't know, any of the metrics that we used before because it simply doesn't make sense, right? What we can do instead, though, we know the actual classes. So when I give it an input image, I know that it's supposed to be, let's say, for example, a digit 5, right? And if it puts it in like classifies it as a digit 5, then it's doing a good job. It's accurate. And if it says, oh no, it's a 3, then it's messed up. So what we can do is to actually compare to see how many correct predicted values we have, right? So I'm just going to call ACC, like for accuracy of support vector machine, set that to 0. And I'm just going to copy whatever I do for like one model for the other model as well, right? So I'm just going to go accuracy of the MLP. That's also set to 0. And what I want to do now is for INP in enumerate of in, let's not do it this way. If I go here, okay, what I wanted to do here, actually, let's do that this way. It's good. So you can see. So what enumerate does is that it returns the index and the actual value, right? If I just go for P in predicted, right? Let's say predicted SVM, right? If I do that, P would be like whatever is inside the thing, and I is the index of that thing. So it actually helped. Instead of like doing something like for I in range of length of predicted, I can do it this way. It's just, it looks nicer and more professional, I would say. So I'm just going to go if P equals Y test I, right? Because that's the index and it corresponds to this P value. So for I10, P would be the 10th element in predicted SVM, and test 10 would give me the 10th element here in Y test. So if that's the case, then increase the accuracy of SVM by 1. So that's plus equal 1. And so that's about it. And I'm going to go if I want to do the same thing here. I can have like a separate for loop, or I could just do it here. I can say if predicted MOP of I equals Y test I, because again, P is now pointing to the elements in predicted SVM. I cannot use it here. I have to use the predicted MLP values. That's why I'm using the index. And I'm saying if predicted MLPI equals that, then in that case, accuracy of MLP must equal 1, right? So it loops through all the predicted values, and if they match, it increases the accuracy of the corresponding model by 1, which is exactly what we want. And after that's done, we can just print the accuracy. So if I go print F statement, I can go SVM accuracy is, okay, what's SVM accuracy? I want it in percentage, so I'm just going to multiply 100. How many correct values do I have? That's a.k.a. SVM. And divide it by length of predicted SVM or predicted MLP, doesn't matter, they're the same size. So that's that, and I can do the same thing. I can do it in the same line, or I can do it like in a separate print MLP accuracy, that's a.k.a. of the MLP. Again, like they have the same sizes, but let's just, for the sake of programming here, I'm just going to change that to MLP as well. And let's see how it works. If I run the code, it says the SVM accuracy is 99.44% and MLP accuracy is 97.22%, right? Let's just add the percentage here, the green statement, which is cool. So in this example, the support vector machine is outperforming the MLP model. But again, you can keep playing with the values in here, right? Like you can decrease that and be like, okay, let's see how it goes. You can increase the number of neurons. Like if I go, okay, use 100 neurons in the hidden layer instead of that. Or like, I don't know, use the LDFGS training model instead, right? We can see like how that changes the performance. Let's see. So it actually like made it worse, right? That is like the same, that stayed the same, but for the neural network, it's at worse accuracy now. But again, like you can keep playing with these values and see how it impact the final accuracy. The one thing that you need to keep in mind is that this value is going to change. Like even if I haven't changed anything in here, let's see. If I run that one more time, I'm getting like 95% accuracy, right? And I'm getting a warning that total number of iterations reached the limit, right? Like it tried, but it didn't converge. That's like basically what the warning is, but you don't really have to worry about that. I mean, you do if you really want to, I don't know, see what's exactly going on. But just for the sake of this example in here, you can see that it's complaining about that. But anyway, it's not the same. And that's the point that I was trying to make. And it's because it's using some randomness in the process. If you want to have reproducible results, you should be able to set a random seed in your code. In that case, like every time that you run the code, it's going to be the exact same thing, doesn't matter what. That could be a really good practice for you. Actually try to do that. Try to add a random seed so that every time that you run the code, you're going to get the exact same results. Anyway, that's about it. That's all I wanted to tell you about the support vector machine and neural networks, of obviously how to use them. As I said, I'll be making a separate video on machine learning courses and just, talk about the details, how we can make those and how they're different and stuff like that. But I think it's enough for today's video. Thank you for watching me. And don't forget to subscribe so that you won't miss our next videos. And you guys have a good one. Take care and bye-bye.